What if you found yourself standing at the edge of a cosmic abyss so powerful, so enigmatic, that it bends the very fabric of reality itself? Imagine looking into a void so dark it swallows all light, a place where time seems to slow, warp, and perhaps even stop. Black holes are not just distant astronomical objects, they are the universe's ultimate enigma, gateways to mysteries that challenge the limits of human understanding. For decades, these invisible titans have fascinated and perplexed scientists, philosophers, and dreamers alike. They lurk silently in the vastness of space, invisible to the eye but detectable by their gravitational grip on stars and matter nearby. Their existence was once theoretical, mere mathematical oddities lurking on the fringes of Einstein's equations. Today, thanks to groundbreaking technology and ingenuity, we glimpse their shadows and hear the echoes of their colossal collisions across the universe. But what lies beyond their curtain of darkness? What happens when anything, a star, a photon, even a spacecraft, crosses the boundary known as the event horizon? It's a cosmic point of no return, where known laws of physics teeter on the brink of collapse. Does matter simply vanish into oblivion? Or is there a deeper story, one that holds keys to quantum gravity, the nature of spacetime, and the ultimate fate of information itself? As we peel back the layers of this cosmic mystery, a landscape emerges that is stranger than fiction. Inside a black hole, gravity crushes all complexity into a single point of infinite density, a singularity where our best theories break down and a new physics may be waiting to be discovered. Could these singularities be seeds for new universes? Or do they represent the fundamental limits of our cosmic understanding? Every black hole is a paradox, a riddle wrapped in the universe's most impenetrable cloak. They challenge our concepts of reality, causality, and existence. They are both destroyers and creators, consuming everything nearby while shaping galaxies, influencing the rhythm of cosmic evolution on the grandest scales. In this journey, we will explore what modern science reveals about these extraordinary phenomena. We will trace the footprints left by infalling matter, decode the subtle signals imprinted on the fabric of spacetime, and confront the philosophical implications of a universe where information might never truly be lost but transformed in ways still beyond our grasp. Prepare to step beyond the visible and into the shadows, where mysteries deepen and answers demand patience, imagination, and a willingness to question the very nature of the cosmos. This is the story of black holes, dark, mysterious, and endlessly compelling, a story that unfolds at the frontier of knowledge and beyond. To begin unraveling the enigma of black holes, we must first turn our attention to the doorway that defines their boundary, the event horizon. Imagine standing on the precipice of a cliff, where the ground beneath your feet disappears into an endless abyss. The event horizon is precisely the threshold. It is the invisible boundary surrounding a black hole beyond which nothing, no particles, no light, no information, can escape the gravitational grip. Unlike any physical surface we might know, it is not a barrier you can touch. Instead, it is a geometric feature sculpted by gravity itself. Crossing this boundary means surrendering to an irreversible journey inward, a one-way passage into realms where our familiar laws of physics begin to falter. This boundary is not static or simplistic. The event horizon is shaped by the black hole's spin and charge, causing it to twist and ripple as if stirred by unseen hands. In rotating black holes, the event horizon is oblate, flattened at the poles and bulging at the equator, creating a region around the black hole where space itself is dragged along in what physicists term frame dragging. Within this swirling vortex of spacetime, the very fabric is twisted with immense energy, compelling matter and radiation into spiraling orbits before inevitably crossing the threshold. Matter that drifts too close to a black hole typically forms what is known as an accretion disk, a luminous, swirling maelstrom of gas and dust heated to millions of degrees as it races inward. The intense friction and gravitational forces within this disk cause it to shine brilliantly across the electromagnetic spectrum, sometimes outshining entire galaxies. Observing these energetic beacons offers us glimpses into the invisible realm beyond, signaling the presence of a black hole where darkness might otherwise reign. But what lies immediately beyond the event horizon? The rules of time and space stretch and twist to their limits. For an outside observer, any object falling into a black hole appears to slow down, its image redshifting and fading as it approaches the horizon. This eerie effect is a consequence of gravitational time dilation. Gravity near the black hole slows the passage of time relative to distant observers. Yet, for the object itself, the journey continues unimpeded, racing toward the inner depths in finite time. On this inward trajectory, theories constructed from Einstein's general relativity predict a dramatic fate, an inexorable convergence to a point where density becomes infinite and volumes collapse entirely, the singularity. But within the boundary of the event horizon, the conventional distinctions between space and time blur. Radial direction, which we perceive as spatial, becomes temporal, compelling all paths to lead inevitably inward. Escape is merely an illusion. Once vanished beyond this veil, the future is fixed toward the singular core. To reconcile these predictions with the laws governing the quantum realm remains one of the great challenges of modern physics. Quantum mechanics suggests that information about particles must be preserved, even as general relativity implies their demise beyond retrieval. This paradox has driven decades of debate, culminating in revolutionary ideas such as the holographic principle. This principle posits that all information contained within the black hole is encoded on its event horizon in a manner analogous to a hologram, capturing three-dimensional details as two-dimensional data imprinted on a surface. Black holes also emit a faint glow, Hawking radiation, a phenomenon predicted by physicist Stephen Hawking in the 1970s. Born from the interplay of quantum effects near the event horizon, this radiation slowly bleeds energy away from the black hole, suggesting they are not eternal but can evaporate over unimaginable timescales. For tiny black holes, this evaporation might occur rapidly, while for the behemoths anchoring galaxies, this process spans epochs far beyond the age of the universe. The implications of these subtle interactions ripple far beyond black holes themselves. They confront us with profound questions about the continuity of the cosmos and the reconciliation of gravity with quantum theory. Observations of gravitational waves, ripples in spacetime caused by merging black holes, have opened a new window into these invisible realms, allowing us to hear these cosmic collisions and test theoretical predictions with unprecedented precision. In these grand black hole mergers, spacetime quakes with energy that temporarily outshines every other source in the observable universe, vibrating the cosmic fabric like a thunderous chorus. Such detections confirm many facets of Einstein's insights but also hold clues to hidden physics yet to be discovered. Each new signal we decode increases our understanding, bringing us ever closer to deciphering how black holes grow, interact, and influence the universe on scales both vast and minute. The journey through black hole science is not merely a quest for exotic knowledge but a pursuit that challenges our very place in the cosmos. It compels us to reconsider the nature of existence, the flow of time, and the potential for phenomena so extreme that they transcend everyday experience. Black holes are not simply celestial curiosities or destructive giants looming in darkness, they are windows into the profound mysteries that bind the universe together, where gravity, quantum mechanics, and thermodynamics intersect in astonishing ways. As we continue to probe their depths through telescopes, detectors, and theoretical insights, black holes remain both our cosmic laboratories and our greatest enigmas. Each discovery reframes our understanding, reminding us that the universe is far stranger, richer, and more captivating than we have dared to imagine. To comprehend black holes is to glimpse the boundary between the known and the unknown, inviting us to venture beyond the limits of human knowledge and into a realm where physics itself is still being rewritten. At the heart of black hole theory lies a captivating tension between the laws of gravity and the seemingly unyielding principles of quantum mechanics. The classic framework that guides our understanding is Einstein's general theory of relativity, a masterful description of how mass warps spacetime itself. According to this theory, when a massive star exhausts its nuclear fuel, the inward pull of gravity overwhelms all other forces, collapsing the star's core into an infinitely dense point known as a singularity. Surrounding this singularity is the event horizon, the invisible threshold beyond which nothing, not even light, can escape. This boundary marks a definitive point of no return, shrouding the singularity in eternal mystery. Yet, this beautifully coherent picture raises profound puzzles when combined with the principles of quantum physics. For decades, the notion of a singularity implied a breakdown of known physics, a place where spacetime curvature becomes infinite and the very fabric of reality unravels. It's a cliffhanger in the story of the universe, signaling that our theories are incomplete. The black hole, as predicted, should be a simple, all-consuming beast described by just a few parameters: mass, spin, and electric charge, according to the Noether theorem. But the quantum world suggests a more intricate narrative. One of the most intriguing developments is the realization that black holes are not entirely black. In the 1970s, physicist Stephen Hawking proposed that quantum effects at the event horizon cause black holes to radiate faintly, now known as Hawking radiation. This radiation implies that black holes can slowly leak energy, and over unimaginable spans of time, potentially evaporate entirely. This revolutionary insight bridged gravity with quantum theory in an unexpected way, yet it introduced unsettling questions. If black holes evaporate by emitting Hawking radiation, what happens to the information embedded in the matter they have swallowed? This dilemma, known as the information paradox, points to a fundamental conflict. Quantum theory insists that information cannot be destroyed, but classical black hole physics suggests it could be lost forever. Addressing this paradox has led scientists to propose bold hypotheses that reshape our understanding of space and time. One compelling idea is the holographic principle, a radical theory that asserts all the information contained within a volume of space can be described by data encoded on its boundary. In the context of black holes, it implies that the seemingly inscrutable interior might be fully represented by phenomena on the event horizon itself. This principle hints that spacetime and gravity emerge from an underlying layer of quantum bits, weaving a tapestry where the familiar three dimensions of space are a projection from a two-dimensional surface. If true, this transforms black holes from inscrutable objects into the key to unlocking the quantum structure of the universe. In exploring the depths of black holes, physicists also confront the dynamic interplay between gravity and quantum entanglement, a mind-bending correlation between particles that exists across space and time. Some theories suggest that the connectivity of entangled particles might be linked with the very geometry of spacetime inside black holes. This interplay proposes an astonishing idea, that the fabric of the cosmos itself could be held together by quantum connections, and within black holes, these connections become woven into the extreme geometry of the singularity, bending our perception of cause and effect. But beyond the confines of theoretical physics, the implications of these ideas ripple into broader questions about reality itself. Black holes challenge our understanding of time, suggesting it might behave differently near their horizons. The passage of time, as described by relativity, slows down dramatically under intense gravitational forces, and approaches a standstill from an outside observer's perspective at the event horizon. Inside, the flow of time and the very sequence of cause and effect become enigmatic, blurring the boundaries between past, present, and future. This profound temporal distortion invites us to reconsider the linearity of time as an absolute truth, nudging toward a more nuanced, perhaps cyclical or branched conception of how events unfold in the universe. The fate of matter crossing a black hole's event horizon also remains a frontier of mystery. While classical theory predicts its inevitable collapse into the singularity, quantum models suggest alternative endings. Some hypotheses propose that the collapse is halted by exotic quantum states, creating a fuzzball of tangled strings or a firewall of intense radiation. Others imagine black holes as portals to other regions of spacetime, a speculative idea that hints at wormholes or Einstein-Rosen bridges. Though these remain unproven and speculative, they fuel imaginations and inspire new avenues of research, urging us to confront the limits of what we can observe and infer about regions forever cut off from direct view. Crucially, black holes serve as natural laboratories for the quest to unite the forces that govern the cosmos. Their extreme conditions are unlike anything replicable on Earth. Intense gravity, bizarre quantum effects, and warped spacetime converge here. Understanding these cosmic enigmas could illuminate a path toward a theory of everything, a framework that reconciles the apparent contradictions between general relativity and quantum mechanics. Each night, as astronomers gaze through powerful telescopes and physicists unravel complex equations, they inch closer to comprehending how the universe functions at its deepest levels. In the end, the main theory that governs black holes is not a closed chapter but an evolving narrative. It is a story shaped by the tension between what we observe and what we can imagine, grounded in empirical evidence yet propelled by the human spirit's quest for knowledge. Black holes embody the mysteries of the cosmos, demanding that we expand our horizons to conceive realities far beyond our everyday experience. In confronting these cosmic enigmas, we are reminded of the vastness of the unknown and of the extraordinary capacity of the human mind to reach into that darkness, seeking illumination where there was once only shadow. Beyond the foundational understanding of black holes as regions where gravity reigns supreme, there lies a captivating realm of subtleties and profound questions, opening new windows onto the nature of reality itself. One of the most compelling scientific pursuits is to uncover what happens not just at the threshold, the event horizon, but deeper within, as matter spirals inward toward the unfathomable singularity. Observations from around the world, through increasingly sensitive instruments, continue to refine our picture. The image captured in 2019 by the Event Horizon Telescope, a groundbreaking mosaic of radio waves from the supermassive black hole at the heart of the galaxy M87, did more than provide the first direct glimpse of a black hole's silhouette. It offered an empirical anchor for theories that describe how light is distorted and bent near these cosmic giants. This observational triumph not only confirmed the predictions of Einstein's theory of general relativity under extreme conditions, but also challenged scientists to explain subtle discrepancies and to envision what might lurk beyond the veil of photons. Remarkably, in recent years, the discovery of gravitational waves, ripples in the fabric of spacetime produced by black hole mergers, has opened a fresh frontier of exploration. These waves carry encoded information about the masses, spins, and dynamics of black holes as they collide and coalesce, revealing complex behaviors never before accessible. Each detected event enriches our understanding of how black holes grow, interact, and shape the galaxies that host them. For instance, some mergers hint at the existence of black holes with masses bridging the gap between stellar remnants and supermassive giants, raising fascinating questions about their origins. Do these middleweight black holes emerge from the gradual accretion of matter, or from the titanic union of countless smaller black holes? The answers could illuminate the cosmic evolutionary pathways that seed the vast structures we observe on the grandest scales. Expanding from the astrophysical realm into theoretical physics, certain speculative yet mathematically rigorous concepts invite us to rethink what lies at the core of black holes. One such idea proposes that the singularity, the point of infinite density, might be replaced by a region of exotic quantum states where the known laws of physics break down or transform. Could this be a gateway to new dimensions or parallel universes encoded within black holes? Models inspired by string theory and loop quantum gravity suggest that the classical notion of a singularity may give way to a quantum fuzz, a restless sea of vibrating strings or discrete quantum loops, blurring the boundary between space and time itself. If true, these insights might recast black holes from mere cosmic cul-de-sacs to cosmic nexuses, where information and energy take on entirely novel forms. The implications of these possibilities extend far beyond astrophysics. If black holes harbor regions where conventional spacetime dissolves, they might offer clues to the long-standing puzzle of information preservation in the universe. According to classical physics, any information about matter swallowed by a black hole is lost forever, a notion seemingly at odds with the fundamental tenet of quantum mechanics that information can never be destroyed. Reconciliation of this paradox has led to profound theoretical advancements. Some physicists suggest that information is not destroyed but is instead scrambled and encoded in subtle correlations on the event horizon, or perhaps carried away by faint radiation streams known as Hawking radiation. This radiation, predicted by Stephen Hawking in the 1970s, provides a tantalizing window into the life cycle of black holes, hinting that they might slowly evaporate over vast timescales, releasing energy and information back into the cosmos. While these revelations challenge our intuition, they underscore black holes' role as crucibles where the deepest mysteries of nature converge. The ongoing endeavor to test and refine these ideas drives innovation across multiple scientific disciplines, from high-energy particle physics to advanced computing techniques. Cutting-edge experiments, such as those conducted in particle accelerators and ultra-sensitive detectors, aim to recreate, in miniature form, the conditions that mirror aspects of black hole physics. Such experiments not only deepen our understanding of fundamental forces but also inspire novel technologies, influencing areas as diverse as quantum computing and materials science. Turning back to the cosmos, the influence of black holes extends beyond their immediate neighborhoods. Supermassive black holes at the centers of galaxies are engines of cosmic transformation, fueling energetic phenomena like quasars and relativistic jets that shape the formation and evolution of entire galaxies. The intricate feedback mechanisms by which these black holes regulate star formation and redistribute matter highlight their profound importance within the cosmic web. This interconnectedness offers a new lens through which to view the universe, not as a static collection of isolated objects but as a dynamic, evolving tapestry woven together by gravity's relentless grasp. Intriguingly, some researchers are now exploring the notion that black holes might play a role in the very fabric of cosmology itself. Certain hypotheses suggest that black holes could seed new universes or act as conduits linking different regions of spacetime through hypothetical tunnels known as wormholes. While these ideas stretch the boundaries of current scientific consensus, they urge us to ponder the possible bridges between black holes and the large-scale structure and fate of the cosmos. Could our own universe be just one among many, birthed from a black hole in a parent universe? Such questions may redefine our place in the vast multiverse and prompt a deeper appreciation for the cosmic cycles of birth, death, and rebirth on a scale incomprehensibly vast. Ultimately, the expanding scientific narrative around black holes exemplifies the relentless human drive to understand complexity through observation, theory, and imagination. Each new insight disrupts previous assumptions, revealing a cosmos that is more intricate and mysterious than ever imagined. As we stand at the crossroads of observation and theoretical innovation, black holes beckon us forward, inviting not only scientific discovery but philosophical reflection on the nature of existence, reality, and our own quest for meaning within the infinite unknown. As we venture deeper into the enigma of black holes, we find ourselves drawn not only into the domain of physics but also into the profound philosophical questions they evoke, questions that challenge our understanding of consciousness, reality, and the very nature of existence. Black holes, those cosmic abysses where the familiar laws of space and time break down, invite us to confront the limits of human knowledge and the frameworks through which we perceive the universe. One of the most striking mysteries centers on what it means for anything, matter, energy, or information, to cross the event horizon, the point of no return. In a sense, the event horizon is a boundary between what can be known and what remains forever concealed. For an outside observer, time appears to slow as an object approaches this boundary, stretching into an eternal freeze. Yet, for the falling object itself, time flows normally until all is lost beyond sight. This paradox hints at the complicated relationship between observation, reality, and consciousness. It poses the question, if different observers experience time and reality so differently, what does that say about the nature of existence itself? Does reality exist independently of observation, or is it intimately linked to consciousness in ways we have yet to comprehend? Moreover, the singularity, the core of the black hole where densities become infinite and our current understanding of physics collapses, forces us to speculate about the breakdown of spacetime as we know it. Here, the fabric of reality seems to unravel, inviting metaphysical reflection. Does the singularity represent an ultimate boundary to knowledge, a cosmic enigma that resists not just scientific explanation but also philosophical comprehension? Or could it be a gateway to new states of existence, realms beyond the constraints of our conventional reality? These questions echo ancient philosophical inquiries about the nature of being and nothingness. Black holes, in a cosmic scale, embody the paradox of existence and non-existence. They are regions where matter and information are thought to be sequestered away from the observable universe, yet the laws of quantum mechanics suggest that information cannot be destroyed. This tension leads to the famous information paradox, which challenges our grasp of how reality preserves or reshapes what falls into these gravitational chasms. It's a modern incarnation of the timeless puzzle. How does the universe balance order and chaos, certainty and mystery? From the perspective of consciousness, black holes might serve as profound metaphors for the human condition. Just as matter disappears beyond an event horizon, parts of our inner lives, memories, experiences, emotions can seemingly vanish into the abyss of the unconscious. Yet, the idea that no information is truly lost invites hope that beneath apparent darkness lies a hidden preservation, a subtle continuity linking what we perceive as fragmented or forgotten. In this view, the black hole becomes a symbol of transformation rather than annihilation, an invitation to consider cycles of loss and rebirth, of change that transcends apparent endings. Extending this metaphor further, one might contemplate whether consciousness itself could be influenced by phenomena akin to black holes. Could moments of profound introspection or altered states of awareness resemble crossing boundaries where ordinary time and identity lose their rigid structure? Could the mind, in its depths, mirror cosmic processes where the known dissolves into mystery, only to emerge anew with different understanding or insight? These are speculative thoughts, but they underscore how black holes compel us not only to expand our scientific horizons but to expand the contours of existential inquiry. In the broader tapestry of meaning, black holes stir reflections on the nature of reality as something fluid and multi-layered. They challenge the classical picture of a deterministic universe, suggesting that information and existence might be far more subtle and interwoven with the observer's role than previously believed. This opens pathways to reimagining reality not as a fixed stage but as an evolving interplay of possibility and perception, where the boundaries between the observer and the observed become ephemeral. Perhaps most humbling of all is the recognition that black holes illuminate one of the fundamental limits of human understanding. They remind us that despite all our technological advances and intellectual achievements, the universe holds mysteries that defy easy explanation. To stand before a black hole, even conceptually, is to confront awe, wonder, and the profound silence of the unknown. It is a call to embrace curiosity without arrogance, to balance skepticism with imagination, and to accept that some answers may lie beyond the horizon of reason as we know it. In this way, black holes do more than challenge astrophysics or cosmology, they invite us into a deeper engagement with the questions that have animated human thought for millennia. What is real? What is eternal? How does the ephemeral weave into the infinite? As we peer into the darkness of these cosmic phenomena, we are invited not only to seek scientific truths but to embrace the mystery itself, finding, perhaps, a reflection of our own quest to find meaning within the vast, shadowed expanse that surrounds us. Black holes, by their very nature, beckon us to the edge of comprehension, inviting speculation that is at once exhilarating and disquieting. Beyond the known lies a realm where the familiar laws of physics begin to fray, where space and time curl into shapes that challenge our deepest intuitions. One of the most unsettling possibilities is the notion that black holes could be the ultimate cosmic erasers, consuming not just matter but also the very fabric of information that defines reality. While this idea might sound abstract, it has profound implications. If information is truly lost inside a black hole, what does that mean for the principle that the universe operates predictably? Are the threads of cause and effect severed in these dark abysses, leaving us with a universe that is, in some regions, fundamentally unknowable? The conundrum deepens with the consideration of the singularity, the enigmatic core of a black hole. According to classical theory, the singularity is a point of infinite density, where gravity crushes everything into an infinitely small volume. Yet, an infinite density defies all physical meaning and threatens to break the equations themselves. What then is this singularity? Is it a physical reality, or a warning sign that our current theories simply reach their limits here? Some imaginative theories suggest that what we call a singularity could be a gateway, a passage to another region of spacetime, or perhaps even to an entirely different universe. This possibility, evocative of cosmic wormholes, fuels speculation about the nature of black holes as potential portals, though such ideas remain speculative, residing at the shimmering fringes between science and philosophical wonder. From a more grounded perspective, the discovery that black holes can merge and produce gravitational waves shakes the very assumptions about cosmic permanence. These cataclysmic collisions release more energy in moments than stars emit in their entire lifetimes, yet they leave behind a black hole whose mass, spin, and charge are the only signs of its violent past. What happens to the intricate structures and histories contained within the original black holes? Are they simply incinerated into oblivion, or subsumed within a new singular gestalt? Such cosmic recycling, cloaked in invisibility, hints at a larger cosmic dance, creation and destruction entwined in a dance beyond the scope of human experience. There is also a more philosophical dimension to the mystery, the nature of time itself near a black hole. For an outside observer, time near the event horizon seems to slow to a near halt, while for anyone falling in, the experience might be fleeting, almost instantaneous. This dichotomy throws into sharp relief the relativity of time and suggests that black holes might serve as natural laboratories for exploring the malleability of temporal experience. Could they harbor echoes of different timelines, or even create conditions where conventional cause and effect unravel? Such ideas challenge the linear narrative of time that governs human consciousness and invite us to reconsider the nature of past, present, and future against a cosmic backdrop. A more speculative but thrilling notion is that black holes could be seeds for new universes. Some cosmologists propose that each black hole might give birth to a baby universe inside, disconnected from our own but born from the collapse within. In this picture, our own universe could have originated from such a collapse. If true, black holes would become cosmic crucibles where universes are spawned, evolving independently, with different physical laws and constants. This concept not only reshapes our understanding of black holes but casts our universe as one bubble in a vast, dynamic multiverse. It is an unsettling yet poetic scenario. What we see as destruction might be, on another scale, creation. Moreover, the fate of matter crossing the event horizon still echoes as a profound enigma. The classical depiction suggests that any matter swallowed by a black hole is irretrievably crushed, however, quantum theories introduce the possibility that what falls in might be smeared or transformed in ways that preserve its essence in subtle, undecipherable codes. If so, could black holes serve as cosmic vaults, storing the universe's secrets encrypted in the fabric of spacetime itself? This speculation touches on the intersection between gravity and quantum mechanics, a currently unfinished chapter in physics, and signals that black holes may hold the key to unlocking a deeper unification of nature's forces. There is also a haunting aesthetic to black holes, one that resonates on an emotional and existential level. They represent thresholds, places where certainty dissolves, and the known universe gives way to shadows. For centuries, humans have sought edges, frontiers to push against. Black holes are perhaps the ultimate frontier, not merely because they lie in distant galaxies, but because they embody the very limits of knowledge and imagination. Engaging with black holes is therefore not just a scientific endeavor, it is a confrontation with the human condition itself, the desire to know, to explore, balanced by the recognition of our finite grasp upon reality. In the vast and silent theater of the cosmos, black holes remind us that some phenomena are not merely obstacles to understanding but invitations to rethink the foundations of thought. They compel us to consider that knowledge may take forms beyond the measurable, that existence might be richer and stranger than the comfortable frameworks we have built. Although they devour light, these cosmic mysteries illuminate profound questions about origin, destiny, and the nature of reality itself. To peer into the depths of a black hole is to encounter a paradox, a space where darkness reveals, where the unknowable invites us to wonder, and where the universe, in its most cryptic guise, whispers the enduring thrill of discovery. As we step back from the swirling maelstrom of gravitational extremes, the story of black holes leaves us with a profound and humbling truth, that the universe is far more complex, and perhaps more beautiful, than our everyday experience would suggest. These enigmatic phenomena challenge our assumptions about space and time, about matter and energy, about the very rules that govern existence. They remind us that reality is layered, with mysteries that unfold in dimensions we are only beginning to glimpse. Black holes are not mere cosmic curiosities, they are crucibles where the known laws bend, offering glimpses of a reality that transcends our current understanding. By studying them, we do more than chart celestial phenomena, we engage in a voyage toward the unknown borders of knowledge itself. Consider, for a moment, the paradox at the heart of the black hole's nature. On one hand, it is a devourer, a cosmic abyss from which not even light can escape, erasing information in ways that seem to defy the very principles of physics. On the other, it may be a kind of cosmic memory, preserving traces of everything it consumes, encoded in subtle imprints on the fabric of spacetime. This paradox pulls us into deeper questions about information, entropy, and the ultimate fate of the universe. Is information lost forever, or does it somehow survive in forms beyond our current comprehension? This puzzle leads us directly into the realm of quantum gravity and the search for a theory that unites the smallest scales with the grandest cosmic architecture. Beyond their scientific implications, black holes invoke a poetic resonance that speaks to human curiosity and vulnerability. They urge us to contemplate the limits of perception itself. When matter crosses the event horizon, we lose sight of it, but this loss is a kind of test, a measure of what it means to witness and measure the universe. The silence beyond the event horizon is not simply an absence, it is an invitation to imagination, to theorize and to speculate about the unknown realms that lie beyond the veil of current knowledge. In their impenetrable darkness, black holes become symbols of human striving, emblematic of our continuous effort to push beyond boundaries, even when the destination remains uncertain. These cosmic phenomena also offer a mirror to our own existence, evoking reflections on time and mortality. Inside a black hole, time dilates, stretching toward infinity as external observers perceive in slow motion what unfolds near its core. This strange distortion prompts questions about the nature of time itself, how flexible it might be, and how intimately it is woven into the structure of space and matter. Just as each life is marked by beginnings and inevitable endings, black holes embody transitions, spaces where the familiar flow of time and causality gives way to something profoundly alien and mysterious. They remind us that existence is fragile, brief, and subject to cosmic forces far beyond our control, yet also part of an extraordinary unfolding of complexity and transformation. Moreover, black holes compel us to rethink our place in the cosmos. They are not isolated monsters hidden in the darkness. Instead, they are dynamic engines driving the evolution of galaxies, influencing the formation of stars, and shaping the very visible structure of the universe. This connection paints a picture of a cosmos alive with interplay and interdependence, where destruction and creation are entwined threads of a larger cosmic tapestry. By understanding black holes, we move closer to appreciating the balance and flow of cosmic life, where cycles of collapse and renewal are woven into the grand narrative of existence. In the end, the mystery of black holes is a testament to the enduring human spirit of inquiry. They challenge us to imagine, to theorize, and to explore beyond the boundaries of the known. Each discovery about these enigmatic objects is not an endpoint but a doorway to new questions, new possibilities, and new horizons. Their story is a reminder that the universe, in all its vastness and complexity, is an ever-unfolding mystery. And as long as we continue to seek, to wonder, and to learn, black holes will remain a profound symbol of that infinite pursuit, the quest for understanding that defines our place in the cosmos. Beyond the well-known aspects of black holes, their immense gravity, their event horizons, and their influence on surrounding matter, lies an intricate world of less intuitive phenomena that challenge even the most advanced scientific theories. For instance, consider the quirks of time itself as it behaves in the vicinity of a black hole. Time dilation, a consequence of Einstein's theory of general relativity, becomes extreme near these cosmic titans. To a distant observer, time appears to slow dramatically for anything approaching the event horizon, almost stretching out indefinitely. It's as if the infalling matter is caught in an eternal slow-motion dance, never quite crossing the threshold from afar. Yet for the traveler venturing inward, time ticks normally, leading to an intriguing paradox where subjective experience diverges wildly from outside observation. Delving deeper, the boundary or event horizon of a black hole can be envisioned not just as a point of no return, but as a complex, perhaps even quantum, membrane. Theoretical developments have introduced the idea of the black hole's surface possessing properties akin to a hologram, a two-dimensional informational layer encoding all that has passed beyond. Imagine a cosmic DVD, where every particle swallowed by the black hole is recorded on this horizon, preserving the fundamental quantum information. This concept emerges from attempts to resolve one of black hole physics' most vexing puzzles, the fate of information. Classical views suggested that anything crossing the horizon would be lost forever, erasing information and violating core principles of quantum mechanics. But the so-called holographic principle and the concept of black hole complementarity hint at a universe far more subtle, where information might be conserved, albeit in an utterly transformed fashion. Moreover, recent research points to the possibility that black holes could act as natural laboratories for quantum gravity, the elusive theory seeking to unify quantum mechanics with general relativity. Their extreme environments, where matter and spacetime are warped beyond ordinary experience, provide fertile ground to test hypotheses about the quantum structure of the universe. The enigmatic singularity, long depicted as a point of infinite density, may instead be something altogether different, regions where traditional geometry breaks down and quantum effects dominate. Some propositions envision fuzzballs or firewalls, exotic states replacing the classical singularity, where the very fabric of spacetime becomes a seething, chaotic foam. Such ideas push physics into realms where our everyday intuitions falter, requiring new mathematics and radically novel conceptual frameworks. Interestingly, black holes are not just destructive consumers of matter and energy, they can also be powerful emitters of radiation, a phenomenon discovered by Stephen Hawking in the 1970s. Hawking radiation arises from subtle quantum effects near the event horizon, allowing black holes to slowly lose mass over astronomical timescales. This process links gravity, quantum fields, and thermodynamics in an elegant synthesis, suggesting that black holes have a temperature and entropy properties traditionally reserved for ordinary matter. Through this lens, a black hole becomes more than an enigmatic void. It assumes the role of a thermodynamic system whose life cycle, from formation to evaporation, follows laws akin to those governing familiar physical phenomena. Examining the cosmic role of black holes further, their influence extends beyond individual galaxies. Enormous supermassive black holes occupy the cores of most large galaxies, including our own Milky Way. These behemoths, millions or billions of times the mass of our Sun, often produce energetic outflows in jets that shape their galactic environments. These jets, composed of highly accelerated particles, can extend thousands of light-years, stirring the interstellar medium and regulating star formation. This feedback loop ties the fate of galaxies intimately to their central black holes, suggesting a coevolution spanning billions of years. The life cycle of stars, the assembly of galactic structures, and the chemical enrichment of the cosmos are all, in subtle yet profound ways, choreographed by black holes' quiet dominion. Yet, the mystery deepens further when considering primordial black holes, hypothetical objects formed in the early universe, distinct from those born through stellar collapse. If they exist, these ancient remnants might provide clues about dark matter, a cosmic enigma that constitutes most of the universe's mass but remains invisible to direct detection. By studying the vibrations and ripples they could produce in spacetime, scientists hope to uncover indirect signals of these elusive entities. Such discoveries would not only illuminate the nature of black holes but might also unlock secrets of the universe's infancy, offering a window into conditions mere moments after the Big Bang. In all these ways, black holes serve as crucibles where the fundamental laws of physics are tested, stretched, and potentially rewritten. They are not just cosmic curiosities but pivotal nodes connecting quantum theory, cosmology, and astrophysics. Their study pushes the frontier of human knowledge, demanding new instruments, theoretical breakthroughs, and imaginative leaps. Each new piece of information gleaned, whether from gravitational wave observatories, high-energy telescopes, or cutting-edge simulations, brings us closer to a cohesive understanding of reality itself. As we contemplate the implications, it is worth reflecting on the philosophical resonance of black holes. They challenge our notions of causality, locality, and even reality's fabric. The idea that entire regions of spacetime can become disconnected from the rest of the universe, that information might be scrambled or preserved in unexpected ways, forces a re-examination of what it means to know and observe. Black holes, in a subtle dance of gravity and quantum mechanics, compel us to confront the limits of perception and the layered complexities beneath apparent emptiness. The journey to understand black holes is far from complete. With each advancement, they reveal new puzzles, new horizons, and new mysteries, continually expanding the boundaries of science and imagination. In unraveling their secret depths, we glimpse not only the workings of the cosmos but also the intricate tapestry of laws and phenomena that shape our very existence. The mystery of black holes, enigmatic and profound, endures as one of the grandest quests of human inquiry, an invitation to explore the unknown realms where space, time, matter, and information converge in the most extraordinary ways. When we peer into the abyss of a black hole, we are not merely contemplating an astrophysical object, we are encountering a profound symbol of the universe's deeper enigmas, a threshold where the known laws dissolve into something alien and inscrutable. Beyond the scientific description of curved spacetime and gravitational collapse, black holes invite us to reconsider the nature of reality itself, not as a fixed, objective stage on which events unfold, but as a dynamic, layered phenomenon shaped by observation, consciousness, and the subtle interplay of time. In everyday experience, We live embedded in a seamless flow of moments, where cause leads to effect in an unbroken sequence. Yet black holes unravel this flow, pulling us into domains where the familiar rules falter. Time near a black hole's event horizon slows dramatically from the perspective of outside observers, stretching moments into near eternity, or perhaps, from the vantage point of the falling observer, compressing what happens outside into a fleeting instant. This distortion forces us to confront a paradox at the heart of temporality. What if the passage of time is not universal, but relative, even subjective? If reality's unfolding is tied to the observer's frame, then the black hole emerges as a cosmic mirror reflecting the fluid, perspectival nature of existence. This relativity of time raises profound questions about consciousness and our place as sentient beings within the fabric of the cosmos. Our awareness is bound up with memory, narrative, and the experience of sequential moments. But if the flow of time can be so radically different in another frame, what does that imply about the continuity of self? Might the singularity at the center of a black hole represent not only a breakdown of spacetime, but also a kind of ultimate convergence, where distinctions collapse and identity dissolves into an undifferentiated state? Though purely speculative, such reflections offer a poetic parallel with certain philosophical and mystical traditions that speak of unity beyond form and time, echoing how black holes reduce spacetime to a point where conventional distinctions cease. Moreover, black holes compel us to examine the limits of human knowledge and the frameworks through which we interpret the universe. They reveal that reality is often stranger than intuition allows, and that our grasp of the cosmos is filtered through layers of conceptual assumptions. The interplay between gravity and quantum mechanics near a black hole highlights the tension between continuity and discreteness, determinism and uncertainty, inviting us to ponder whether the ultimate nature of reality might be a web of probabilities, correlations, and emergent patterns rather than fixed objects and immutable laws. In this light, black holes can be seen as cosmic laboratories for exploring the relationship between information and existence. The question of what happens to information swallowed by a black hole is not only a puzzle of physics but also a metaphor for how knowledge and meaning might persist or transform in the face of overwhelming change. If information is never truly lost but encoded in subtle ways, then perhaps the universe itself is an interconnected archive, where every event, no matter how cataclysmic, leaves traces that reverberate through the cosmic fabric. This perspective encourages a view of reality as deeply intertwined and holistic, a network of events and influences whose history resists final erasure. The meditative silence that surrounds a black hole invites us to reflect on human meaning against the backdrop of cosmic vastness. These objects are both destroyers and creators, where matter is crushed and reshaped, where familiar landmarks of space and time dissolve, and where the universe reveals its capacity for transformation on scales both immense and infinitesimal. Facing such extremes can evoke feelings of insignificance, yet also wonder. It challenges us to place our lives within a context that spans the infinite and the infinitesimal, reminding us that meaning arises not from permanence or certainty, but from engagement, curiosity, and the courage to seek understanding amid mystery. Ultimately, the mystery of black holes is a mirror held up to human consciousness itself. They are not just distant phenomena to be catalogued and explained, they are gateways to deeper inquiry into the nature of reality, perception, and the flow of time. As we continue our exploration, we discover that in confronting the dark heart of the cosmos, we also confront the shadows and possibilities within our own minds. In this dialogue between the universe and ourselves, the black hole takes on a symbolic role, a cosmic riddle inviting us to transcend the boundaries of experience, embrace uncertainty, and uncover new dimensions of meaning beyond the visible horizon.